Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Up until now, we've treated y as a function of x. But in real-life applications, x and y are usually partners in motion. Most of the time, they're both changing with respect to time. This is the world of related rates. By using implicit differentiation, we can uncover the hidden links between different speeds in a single system. Now, before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. So let's start with a game plan before we dive into the problems. Every related rates problem follows the same 3 steps. First, we want to determine the equation that relates the given quantities, and usually we want to draw a diagram so that we can visualize it. And once we've set up the equation, our second step is to differentiate both sides using implicit differentiation, and we're going to differentiate it with respect to the independent variable. And our third step is to fill in any known data values and then solve for our missing quantity. So let's take a look at how to apply those 3 steps with our first problem. So here we have a rectangle where our length is increasing at 3 centimeters per second, and then the width is increasing at 2 centimeters per second. And then at some point in time, the length is 10 centimeters and the width is 5 centimeters. So now the question is, how fast is the area increasing? So at first glance, it seems like we have a lot of different values to work with here. But remember that our step 1 is to write down an equation that relates the given quantities. So here, we are working with the area of a rectangle, and we're given some information regarding the length and width. So the equation that we're going to set up is going to be the area of a rectangle is equal to the length times the width. Now for our step 2, we're going to use implicit differentiation and differentiate both sides with respect to the independent variable. And most of the time, that's going to be time. And you can get a hint on what that is by looking at the units here. So we have centimeters per second. So that per second part tells you that things are changing with respect to time. So this means we're going to take d by dt of both sides of this equation. So we get d by dt of A is equal to d by dt of the length times the width. So now the left side, that's just going to be dA dt. And then the right-hand side, we're going to have to use our product rule. So this is going to be dl dt times w plus L times dw dt. And then finally, our step 3 is going to be substituting in the values that we already know. So from the problem, we know that the length is increasing at 3 centimeters per second. So that means our dl dt is equal to 3. We know that the width is increasing at 2 centimeters per second. So that means dw dt is equal to 2. And then at this particular moment in time, the length is 10 centimeters, meaning our L is equal to 10. And then finally, our width is 5 centimeters, which means W is equal to 5. And since the question is asking for how fast is the area increasing, they're asking us for dA dt. So now, substituting these values into this equation here, we can find that dA dt is equal to 3 times 5 plus 10 times 2, which means the area is increasing at 35 centimeters squared per second. Now let's take a look at our next example. Here we have oil spilling from a tanker, and it's forming a perfect circle. Now the radius is growing at 0.5 meters per minute. And the question is, how fast is the area growing when the radius is 20 meters? So because it's asking for how fast is the area growing, we're looking for dA dt. So same thing, we're going to start with our step 1, which is setting up our equation. So now we are working with a perfect circle, and then we want to find how fast is the area growing. So the equation that we're setting up is the area of a circle. and that is going to be a is equal to pi r squared. Now step 2, we're going to differentiate both sides with respect to the independent variable. And then looking at our unit here, it's meters per minute, which means that our independent variable is time. So we're going to go d by dt of our left side is equal to d by dt of our right-hand side, which means we get dA dt is equal to, so pi is just a constant, which means we can pull that out in front. And then the derivative of r squared with respect to t, we're going to have to use our chain rule. So this is going to be 2 times r times dr dt. And now finally, our third step is to substitute in all the values that we know. We know that the radius is growing at 0.5 meters per minute, which tells us dr dt is equal to 0.5. And we want to find dA dt when the radius is 20 meters. So this means at this particular moment in time, our r is equal to 20. So now substituting those values in, we get dA dt is equal to 2 times pi times 20 times 0.5, which means our area is growing at a rate of 20 pi meters squared per minute. And now let's do a recap of what we covered in this video. We saw how important chain rule is in related rates, because every time we take a derivative of a variable like the area, the radius, or the height, we have to attach a rate term like dA dt or dr dt. And the reason is because everything is changing with respect to time. And in related rates, we need to understand the difference between a snapshot and a constant. You never plug in your snapshot numbers until after you have differentiated. So a snapshot number would be something like when the radius is equal to 20. It's called a snapshot because the radius is not always 20. It's just that in that particular moment in time, the radius is 20. So we always want to differentiate our equation first and then plug in our snapshot number. Otherwise, our derivative will incorrectly drop to 0. Now it is your turn to give this a try. Can you figure out the solution to the question that's on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.